Hi there, my name is Caitlin Daly, and today I will be introducing the GFL-NMA-R package, which may be used to identify similar parameters in network meta-analysis. The GFL-NMA package enables users to implement a data-driven approach to sensibly reduce the number of parameters in a network meta-analysis model. Depending on the presence of between-study heterogeneity, aggregate data on the relative effects of treatments may be modeled in various ways. The fixed effects NMA model is the simplest model, which only consists of parameters that define the relative effects of treatments K versus a reference treatment 1. The random effects NMA model additionally captures any between-study heterogeneity, typically through a single parameter tau. Network meta-regression, which is an extension of network meta-analysis, may attempt to explain heterogeneity by modeling the relative treatment effect covariate interaction terms for each relative treatment effect K versus 1 and each covariate P. Any heterogeneity that is not explained by the NMR model may be captured through tau. The GFL-NMA-R package leverages generalized fused lasso to shrink parameters in such models to 0. So why might you want to reduce the number of parameters in a model? Well, for one, you may not have enough data points to estimate all parameters in a single model. For example, consider a network consisting of 10 treatments. A fixed effects NMA model will estimate 9 parameters, while a random effects NMA model will estimate 10. If you want to adjust for 2 covariates, in a full network meta-regression model, the number of parameters that you have to estimate jumps up quite a bit. In addition, you may wish to reduce the false positive rate in your analysis, and this is the proportion of treatment contrasts that are flagged as significantly different, when in truth there is no difference between these treatments at all. So the GFL-NMA package was developed following the derivation of a generalized fused lasso framework for reducing parameters in NMA by my colleagues at the University of Waterloo. This framework was designed for contrast-based NMA models. So these are those that synthesize relative rather than absolute effects. And the framework focuses on situations where data is inputted on the contrast level. So for example, mean differences or log odds ratios. And the framework is currently limited to the frequentist setting. To sensibly reduce the number of parameters in a model, the following GFL-NMA problem is solved through a computationally efficient algorithm, which is available through the GenLasso-R package. In this problem, the relative treatment effects, as well as their pairwise differences, are penalized by some parameter lambda. When lambda equals 0, no parameters are penalized, and then the traditional contrast-based model is estimated by minimizing the residual sum of squares. Essentially, the GFL-NMA solution will pool any relative treatment effects for which there is insufficient evidence of their difference. Okay, so how do you put this into practice? There are a series of 5 main steps, the first 4 of which can be implemented using functions available in the GFL-NMA package. First, we need to derive the inputs required for GFL-NMA, and then we can solve the problem. Then we select the best fitting model that is captured along the GFL-NMA solution path, and then we recode the treatments to match the treatment configuration of the best fitting model. As a final step, you may rerun the network meta-analysis with the new treatment configuration, and this can be conducted using any software of your choice. To illustrate the package, I will use a dataset consisting of 7 trials investigating 5 treatments for Parkinson's disease. One of these studies is a 3-arm trial. The outcome is mean reduction in time off work, and we are interested in synthesizing the differences in this outcome between treatments. So to derive the inputs for GFL-NMA, we need to input a data set that contains all pairwise contrasts in each study. This is a requirement by the NetMeta package, which is used internally by the PrepGFL data function to first estimate the between study standard deviation prior to solving the GFL NMA problem. So notice in our single multi-arm trial, we've got all three possible contrasts. We input this data into PrepGFL data, and we specify the columns that contain our relative treatment effects, the corresponding standard error, the columns that contain the comparator and intervention treatments within each studies, and the study labels. We also need to specify which columns contain data that may be used to estimate the covariance between relative effects in a multi-arm trial. So in this example, the standard error of the mean outcome in the comparator arm was used to estimate this. Additionally, we need to specify whether we plan to fit a fixed, random, or multiplicative effects model. In this example, because the between study standard deviation was estimated to be 0, we fit a fixed effects model. So PrepGFL NMA will output a list of 3 R objects. The first is a data set or a data frame consisting of contrast relative to trial-specific reference treatments. So note that in the multi-arm trial, we only have 2 contrasts versus the same comparator, the placebo. Additionally, PrepGFL data will output the variance-covariance matrix corresponding to the outputted data. And this is defined based on whether we specified a fixed, random, or multiplicative effects model. PrepGFL data will also output what the underlying model is as a reminder to the user. The second step is to solve the GFL NMA problem, and we use the solve GFL NMA function to do this. For this function, we need to specify the estimated relative effects, which is given in the data frame outputted by PrepGFL NMA, the corresponding variance covariance matrix, the treatments being compared, the reference treatment in the network, and then we need to indicate whether we want to consider the full model with no parameter pooling as a candidate model. Here we can see visually how the solution to the GFL NMA problem unfolds. So in the full model, when lambda equals 0, each relative effect is estimated separately. And then as lambda increases, the relative effects are shrunk to 0. Treatments with similar effects are pooled. And note in this diagram, the dashed vertical lines indicate points where parameters were pooled or unpooled. Next, we need to assess the fit of each model at points of parameter pooling or unpooling along the solution path. And tabulate solution path summarizes this nicely for us, giving us a variety of penalized fit measures to compare. By default, the corrected AIC is used to benchmark the models. And for the model with the smallest corrected AIC, we can see that the relative effects of treatments 2 and 5 were pooled and the rest were separate. After selecting the appropriate model, the treatments need to be recoded if any of them were pooled. We can use recode GFL param to do this. So this function requires the data frame you will use to rerun the NMA. And because I will be rerunning the NMA with the NetMeta package, I used the original data set with all pairwise contrasts in the multi-arm study. We also need to input a vector of the parameter estimates for the selected model, and this may be extracted from the outputs of the GFL NMA solution. PAR groups lists the indices of the parameter groups involved in the full model, and this is outputted by solve GFL NMA. And then finally, we need to specify the corresponding treatment codes. So recode GFL param will then output the original data set that you've inputted with the recoded treatments appended. Finally, you may rerun the NMA using the reconfigured treatment codes. I use the NetMata R package to do this, which fits a frequentist model. And because of this, I need to remove all contrasts that compare treatments that have been pulled from the data set. For those that may be interested, this is a league table that compares the NMA estimates from the full model against the estimates from the selected GFL NMA model. Okay, I have a couple minutes to quickly motivate and provide an overview of the GFL process for network metaregression. So in network metaregression, parameter reduction is often employed, and this is usually done by restricting covariate adjustment to one covariate at a time, and by employing a shared effect modifier assumption. So this assumption assumes that for a given covariate, the relative treatment effect covariate interaction term is the same for a group of treatments. For example, this is often done for those that belong to the same drug class. But what if we had no information to justify this assumption? So for example, what if we were dealing with non-pharmacological treatments? So when there is no prior knowledge or evidence to justify treatment groupings, then it may be best to let the data decide, and this is where GFL NMR may be useful. So this is joint work with my colleague Audrey at the University of Waterloo. We formulated a framework that enables GFL for network metaregression. This is very similar to what we saw for the GFL NMA. Now we are additionally penalizing interaction terms. Note that we have a different penalization factor for the relative effects and the interaction terms. When there is insufficient evidence of a difference between interaction terms, the solution to this problem pools them, which in a sense allows the data to determine which interaction terms should be shared. In addition, the interaction terms are shrunk to 0, so the solution simultaneously performs variable selection. The steps to solving GFL NMR problems are very similar to those for GFL NMA. And so we can use similar functions, but we need to specify additional information on the covariate data. There are, however, some key differences between GFL NMA and GFL NMR, and I will briefly mention them now. So for one, because we are using a frequentist approach, the between study standard deviation cannot vary along the solution path under the current framework. We don't want this to be the case because we want to use network metaregression to try to explain and reduce between study standard deviation. So to get around this, we propose capturing any unexplained heterogeneity through a multiplicative effects model rather than a random effects model. And we can show that the solution to the GFL NMR problem does not depend on the multiplicative heterogeneity term. When it comes to solving the GFL NMR problem, note that we now have to specify covariate data, any pre-specified groupings for interaction effects if one so chooses, although if that's the case, then you might not need to conduct a GFL NMR analysis. Gamma is an important thing to consider. This is the ratio of penalty terms for the interaction terms over the relative effects. If this is 0, then we only penalize the relative effects. If this is infinity, we only penalize the interaction terms. There is also an option for centering and rescaling. If there's more than one covariate that we need to adjust for, they need to be scaled down to the same scale to ensure fair penalization. For a full demonstration of GFL NMR, please see the vignette within the GFL NMA package. Thank you very much for your attention. Here's a link to the package on GitHub, and please contact Audrey or I if you have any questions. We will be posting a manuscript on arXiv soon, so keep an eye out. Thank you again.